Okay, we talked most recently about electromagnetic induction and specifically Faraday's law. And we talked about how if you have a changing magnetic field or changing magnetic flux, you can induce a current in a current carrying wire. Now, Lenz's law talks about what direction is the current going to flow. And what we know is that it's always going to flow in such a direction that the magnetic field set up by the new current is going to oppose the change that created it in the first place. So we're going to do a bunch of practice problems, and the way this has to work is when you come to a new scenario like this one, you're going to pause the video, figure out the answer for yourself, and then turn it back on and listen for the response so you can understand what's going on. Okay, so go ahead and pause the video, figure out the direction of the magnetic field. Starting right now, like think of a little spot right here on this wire and think, is the current going to be going up the wire or down the wire? And that will help you think through it. So go ahead and pause the video and then come back when you're ready for an explanation. Okay, hopefully you're back. We'll start by drawing the magnetic field lines around a bar magnet, and it looks something like this, where you have the lines of magnetic field coming out of the magnet. So if you start moving the magnet in towards the coil, what you can think of is the magnetic field lines that are coming out are going to be headed towards that little coil. So if we draw a little cross-section type of picture of that coil, and I draw a little loop, what's going to be happening is you can think of magnetic field lines going into the coil, so like a bunch of little X's. And so now you understand that that's changing and getting more intense. You can think with the right-hand rule about the direction the current has to be. And if you use the right-hand curly hand rule, you realize that by having a current that goes up the coil like this, you're going to be creating a little magnetic field that's going to come out at you. So put your thumb in the direction of the current, wrap your right hand around the coil, and you're going to see the magnetic field lines come out at you. And that's what you want, because if the change is to get more field lines inside the loop going with little X's, you want to have dots to cancel them out. So in this case, it's going to be going up, right over here on this side. So all of the currents are going to be flowing this way. Okay, let's try the next one. Okay, again, check out the scenario, try to figure out what direction the current is going to travel, and then come back for an explanation. Just so you're aware of what's going on, this over here represents the magnetic field. You're taking a square area and you're moving it into the magnetic field. Has a velocity v, so as you're moving it, think about the flux on the inside of the loop and how it's going to be changing. Okay, hopefully you're back. So hopefully you'll realize when you bring this loop over the magnetic field, what's going to be happening is the number of X's is going to be gradually increasing inside the loop. So if that is true, what direction is your current going to go such that it will oppose the change? Well, if you use your right-hand rule and you have the current going this way, then you're going to create magnetic field dots coming out of the page at you, something like that. And that will be opposing the little X's that you're growing or increasing as you go moving your little coil into the magnetic field. So the idea is your magnetic field, your coil is going to be in here, you're going to be picking up X's, you want to oppose those. So you would want to have this current be going in the counterclockwise direction. Okay, next one. Pause the video, figure out what's going on, and think about which way the current's going to go. So maybe think about right here on the loop, which way is the current going to travel? Is it going to go to the right or is it going to go to the left? Okay, so with this particular magnet, think about magnetic field lines are going to go like this again. In this case, they're going to go from north to south. So from north to south. So as you're moving it, this is really hard to kind of consider, but as you're moving this whole thing downwards, then it's what's actually happening. It's like more and more magnetic field lines are going to be going inside the loop in this direction. So as the magnetic field strength inside is going in this direction, which is what's happening as you bring this bar magnet close. Now you got to think about which way the current's going to go. So I'm just going to erase this. Let's see if I get it to erase, because it looks deceptive. So in other words, there, the magnetic field lines are supposed to be going inside the loop, not across the front of it. Okay, so as those lines are increasing inside, if you have your current go this way, then using the right-hand curly-hand rule, you would be putting more magnetic field lines inside. So that's not good. That's not what you want. So instead, you think about how instead it's got to be going this way, because that's going to set up a magnetic field due to this current that's going to have it go down and basically oppose the change that's happening from the magnet being inserted into the loop. Okay, next one. We've seen this one similarly before, but go ahead and try it now. Figure out what direction it's going. Okay, in this case, we have magnetic field lines that are coming in this way because, remember, they go out of the north and into the south. So as you have these arrows growing, you have more and more of them. The closer you get, the more intense the magnetic field, so you're going to get more lines inside the loop. So that means that your current has to be flowing this way, because you want to oppose the change. So you want to set up little magnetic field lines that are going to be going in this direction on the inside of the loop. Next one. Okay, so this is a little bit weird, but what's happening here is you have, these are little metal rails. And then you have a wire with a resistor, and it looks like this. So you have this metal rail. And then what you can do is take this whole sort of yellow thing right here, and you can slide it to the left or you can slide it to the right. And that will effectively change the area that is inside the area that is inside here. It's going to increase that area. So by having this little yellow bar slide to the right, you're not changing the intensity of the magnetic field, but you are changing the area. You're increasing the area. And by increasing the area, you are changing the flux. So how is that going to affect the current? So think about, you're going to get more X's, and so you want instead to have to replace those X's with dots inside. In order to get dots inside, then you need to have a current that's going to be flowing in this direction and in that direction. Hang on, that's totally wrong. It's not that way, it's going to be going this way. There we go. Because that's what the little arrows are showing you too. So as you go this way, right-hand rule means that you're going to have little dots coming out at you, and that's what we want, because we want those to oppose the X's that are increasing. Okay, next one. All right, now we have a loop, and if you look what's going on, a coil moves to the left. So do you see how these are spread out up here, but then they're close together over here? And that would mean that you're going from a less intense magnetic field into a more intense magnetic field. So as you take this coil and you move it to the left, what's happening inside the loop? And so what's happening inside the loop is you get a stronger magnetic field or more flux. And so in order to compete against that more flux, to oppose it, then you want to have current going this way. Because current going this way is going to generate the dots coming out at you, and you want more dots to oppose the fact that you're going to get more X's. So this one is going to be going counterclockwise. Okay, and that concludes our Lenz's law practice. All right, we talked a little bit about this in class, eddy currents. Eddy currents are what happens when you take a metal or a conducting material. It doesn't need to be magnetic. It could be copper, it could be aluminum, it could be really any metal. And then you put it in the vicinity of a magnetic field. In other words, down here there's a south that you can't see, but there is a south down here. And so I can draw that. You have a magnetic field going from north to south. By taking a sheet and pulling it through the magnetic field, you induce these little small little loop currents. And those little loop currents are called eddy currents. And those little eddy currents, they create a magnetic field that oppose the change. So over here on this side, they create magnetic fields that are going up, because that's the direction of the loop. And then over here, they create magnetic fields that are going down. So as you're moving to the right, you get a more intense. I'm sorry, like over here on the outside, you're leaving the magnetic field, which means you're losing magnetic field lines, so you want to put them back. And over here on this side, you're coming into a magnetic field, and so you're increasing your magnetic field lines, so you want to oppose by having the opposite. So you create these little loops. So one way to, engineering perspective, prevent that from happening is to put little slices in the metal, little gaps, that will prevent those little currents from running around in circles. That's why we had the little strips in there. Sometimes in metals we actually laminate them. So we'll have a sheet of metal, and then we'll have like an insulating glue, and then we'll have another sheet of metal. And so by laminating them like this, you prevent any little currents from circulating around. So then you won't get a little eddy current that goes around in a circle. And that will create obstructing magnetic fields. Okay. So let's take a look at some example problems. Oh, here's another Lenz law problem. A loop of wire in the plane. This one I didn't go to your diagram. You have to come up with it on your own. So come up with your own diagram and figure out, excuse me, in which direction our current is going to flow. Okay, so we have our loop of wire. We're bringing our loop of wire into our magnetic field as it goes this way. So then you're going to, in a few seconds, you're going to have a loop that looks like this, with increases, X's on the inside. Since you have an increasing magnetic field that's going into the page inside the loop, you want to create little dots to make them go away. And so to get little dots, you're going to have your current going in this direction or this direction. So that would be counterclockwise again. Oh, I guess there was another part of the question. I should go back to that. It said, repeat for the case of the loop moving out of the field. So once you take that field and you move out, basically the current's going to reverse direction to put the magnetic field back in that it's losing, meaning it's going to be going clockwise when it's on its way out. Okay. So here's a Faraday's law problem, a quantitative problem. Find the average EMF induced. Remember, EMF is the same as voltage. Induced in a circular coil of wire with 20 turns and a radius of 0.15 meters. So radius means it's going to be a circle. So we're going to have a circular coil. Well, I already said that. If the angle between the normal to the coil and the 0.4 Tesla field changes from 45 degrees to 0 degrees. So that's where the change is happening. It's going to be in the change of the angle. It goes from 45 to 0. Everything else is going to be held the same. So that's how we're going to get a changing flux. So let's calculate the EMF. We'll set the equation up for you. So here's the idea. Remember, EMF, again, according to Faraday's law, is minus N times the change in phi over the change in T, which is the change in magnetic flux. Okay, so, and flux, remember, is AB cosine theta. So we need to know the number of loops, and then we need to know the area, the magnetic field, and then we need to figure out how is the angle changing. So remember, it's going to be final minus initial when we write the equation. So let's write it out with the numbers we have. I have EMF is equal to minus 20, that's the number of loops, times pi r squared, since that would be my area of my loop, times 0.4 Tesla. Now, keep in mind, all of those things, the radius doesn't change, the magnetic field doesn't change, but the angle does. And we want to go final minus initial. So since it changes from 45 degrees to 0, we want to go final, which is the cosine of 0 degrees, minus the cosine of 45. Take all of that and divide by the amount of time, 0.5 seconds. So hopefully you have a calculator and you can evaluate that and verify that you should get that the EMF is negative 0.33 volts. Okay. All right. Let's talk about some applications of electromagnetic induction. One is like a throwback, and then the other three are more timely, I should say. So, a tape recorder, the old cassette techs. We used to make tapes for our friends. That was a way of showing your love, is you'd pick your best songs and you'd record them from you'd play them from your phonograph, and then you record them on your little tape, and then you record a new song. So it was sort of like the old-fashioned way of creating a playlist, and it took a really long time. So if you made someone a tape, that meant you meant something to them, or they mean something to you. Okay, so how does it work, though? We have a little electromagnet, and then we have down here like a little piece of chromium-coated, basically a plastic strip, and it had like a magnetizable material. And you create a little electromagnet, and you would send in a signal through a wire, and that signal would set up a magnetic field that would go in one direction, and then it would switch and go the other direction depending on the signal coming in. So it could be, the signal could be sinusoidal, it could be positive and negative, and so this electromagnet is going to be constantly going back and forth in terms of its magnetic intensity. And this ferromagnetic material is going to carry that magnetic field down to this little tip right here, which is pressing up against or right next to this magnetic tape. And so as the tape would be sliding along, as it would be moving past your electromagnet, it would be basically changing the domains. This electromagnet down here would be changing the domains of the tape sinusoidally, or however consistent the input was coming from here. It would be revealed recorded on the tape down here. Then when you wanted to do playback, you basically have a very similar electromagnet, except this one would be sensing. So now you'd run your tape, and your electromagnet would be, you wouldn't have a signal turned in here, but you'd have a signal that would come out. So the electromagnet down here would sense the electromagnetic field changes, so it would cause this change of electromagnetic to go this way, and then it would go that way, and so forth, with how it was sinusoidally, the way it was recorded, and then that same magnetic field would be carried to this coil, which would then be sent to an amplifier that would amplify that signal strength, and then play it through a set of speakers. So that's the idea of a little cassette tape recorder. Also video tape recorders, they work similarly. There's your playback, so I'll just skip ahead because I just talked about these, but there's the slides. Okay, so this is actually not that uncommon from the way your doorbell works today. So we have a doorbell switch. We have a circuit, and over here is where you have a little button that you push, and when you push, this little metal piece makes contact with the piece below, and it like closes the switch. So now you can have current flowing. And so the current starts to flow, and it comes through here, and it comes through here, and it goes through these coils around this magnet. And this becomes an electromagnet. And because this becomes an electromagnet, and we have some magnetic material right here, it's going to suck in that magnetic material and pull it over to the left. Which means that when it does, it's going to go bang. Let me hit the slide. It's going to go bang, and this little hammer down here is going to hit the bell and go ding. And then, once it gets pulled, it's going to break away from right here. It's going to break away from this little contact. And so as soon as it breaks away, then the current stops, and then the electromagnet releases and lets it go, and so it flies back. So by pushing the button, you cause it to hammer and then flip back. So really quickly, it's just going to make a ding. Now, if you hold if you hold this down here, you get a sense that it's going to go ding, 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 ding while you're holding it down. Okay, moving on. A couple more slides, just kind of show what happens in the contact switching off. Okay. GFCI circuit. Now, we've talked about this before. This is the kind of special circuit that you have installed in your bathrooms or near your kitchens. Electric code requires that you do that these days. A GFCI circuit stands for ground fault circuit interrupter. And so the idea is this. You have a special little circuit, and it's right here, and this is like a little loop that comes around an iron ring. Then you have your normal circuit behaves that you have current that goes in, and then it flows back out. So you have current going in a full circuit, goes out and then comes back. And those two magnitudes of the current are going to be identical. So whatever goes out is going to come in. Now, if it turns out that the current in 2 exceeds the current in 1. So why would that happen? Like you're flowing something out, but then you have a break, and maybe your circuit touches water, or the wire splits and you get a short circuit. In other words, you're going to get a boost or an increase in current on one side, but not returning. When you have a differential in the two currents, then, well, right now when they're even, the magnetic field by these two different circuits basically balance each other out and cancel out. But when they become uneven, then let's say you have a really strong current going this way and none going the other way, you're going to set up a magnetic field in the vicinity of this coil. And the magnetic field that changes near this coil is going to induce a current that goes through here and it gets a little circuit running. So that's going to induce a current, and it trips a circuit, and when that senses by having a current flow, then it's going to open up the circuit and shut it down so that no more current can flow. So in a very short period of time, once you get this current that's overloading or too much, one is more than the other, it's going to open the circuit and shut down current flow at all. That's to keep you safe in water-rich environments where there's electricity flowing. Okay, now, motors and generators. This is a motor. We have looked at this before. We've talked about how if you have a battery and you have current flowing through your circuit, it's going to be going in this direction up here, and that's going to create a force. Let's say if this was north and this was south, we've talked about how that's going to create a little torque because that's going to push this side and it's going to push that side, and this thing is going to want to rotate. So this is where you have electrical energy from your battery, and it converts it to mechanical energy. It starts spinning, so it's a beautiful thing. Now, that's just a summary. Now we're going to do what's called a generator, which is the reverse. In this case, we're going to have mechanical energy in, or we have a person in this case cranking the coil, and what you're going to get out is electric energy. So how does that work? It's very similar to how a motor works. You have a magnetic field. Let's say this is north and this is south. And now you think about the area inside that coil. And if you think about the area inside that coil, let's have our magnetic field lines are going this way, from north to south. And the lines that cut through that area are going to be constantly changing as you rotate this coil around. So it's going to be wide open, you're going to get lots of magnetic field lines, and then it's going to be smaller and smaller until there's none when it gets to vertical, and then it's going to open up again, you're going to get more. So by cranking this thing around with this loop inside this magnetic field, you have a constantly changing flux. And when you have a constantly changing flux in a magnetic field, I'm sorry, when you have a constantly changing flux, you can generate a current or an EMF, and you can light up a light bulb. That's what a generator does. So we think about Faraday's law of induction. EMF is minus N times delta flux. This is flux right here over delta T. By having a crank like this with a coil, the area of the coil doesn't change. It's not getting smaller or larger. It's just fixed. It's a rigid coil. The magnetic field doesn't change. It is going to be the same all the time, going from north to south. And then cosine theta is going to constantly change. So it's basically cosine theta changes with time. So as it constantly changes, you're going to get an EMF. And that EMF is not going to be constant. It's actually going to be time varying. It's going to be a maximum value and then a minimum value. Basically what you're going to get is a little hint and alternating current. Because you're going to get maximum change and you're going to have minimal change. So as you are cranking this thing around, you're going to generate, around and around and around and around and around, you're going to generate a time-varying EMF or current. Okay, last couple slides. So here's the idea. When you have your generator, you have your coil in your magnetic field. Remember, the field lines are going to be coming through the center like this. When you are at the vertical position, you have your maximum area. So the most area in here, so that would be your largest flux. And then as it starts to rotate, notice that flux gets a little bit smaller. and then it rotates still. Now you're horizontal, that flux has basically gone to 0. So this is the flux. So it's gone from up here, where it is max, down to here, where it is 0. And then it opens up again, and you get more, and then it goes back to the maximum. So you have this cycle of from maximum here, to minimum here, back to maximum here. And it's just going to continually change. Okay? So you go from max to min to max to min. So the effective area within a loop at different rotational angles. So even though the area of the loop doesn't change, the effective area through which magnetic field line cuts do change. So it turns out when you have, and think about why this is true, when you have that maximum flux, that is when you have minimum EMF. Now that doesn't sound intuitive at all. It seems like if you had the maximum flux, you'd have the maximum EMF. But remember, it's not the flux that affects the EMF. It's the change in flux. Okay? It's how fast is it changing. So when you are at vertical, you're actually not changing very much. But when you're here, when you're at horizontal, you're going from having no flux to some flux. That's a really big change. So that's when you're going to get your maximum value of your EMF. Again, you're at vertical, you get 0. You're at horizontal, you get max. You're at vertical, you get 0. So you get a sinusoidally changing magnetic field. And if this is confusing, it is to every student who ever starts to learn about this. It's just going to take a little bit more thought, a little bit more time to figure it out. And that's where we're going to conclude our lesson today, and we'll pick it up again tomorrow, talking more about alternating currents and generators.